Ah, welcome. Now that we have long traversed the long problems of a roller coaster, solved for the PEs and the KEs at various spots. By the way, um, some people even noticed that I drew one of the roller coasters, roller coaster number one, in the last assignment, improperly to scale. I had a point where the values, the heights and velocities didn't match the picture. And that's 100% true. I should have done better. I think I switched them in my mind, and people were recognizing and they were getting tripped up. They're like, wait a minute, the roller coaster's higher here, but it has a lower PE. That doesn't make sense. Did I screw it up? No, you didn't screw it up. I drew it wrong. But good catch. I like that. I like the thinking. I like the analysis. We're really starting to kind of understand these concepts. We're not just blindly plugging numbers into equations. We're thinking about, does this make sense in the context of what we have? And that's a great segue to start with what we're going to do today, which is energy and kinematics. So you may remember, it seems like ages ago, when little Susie would stand on the edge of a cliff and drop an object. So what we have here is, I would say she's down a cliff, she'd drop her tennis ball. So we got a picture of a guy who's jumping off a giant cliff into the water. And we know that, like little Susie dropping the tennis ball, this guy falling, it doesn't matter the object, that gravity is going to speed it up as it falls down. And it's going to, as it gets closer to the ground, it's going to speed up. Now, what I'm saying is that instead of thinking about it in terms of velocity and displacement, think about it as kinetic energy and potential energy. If you think about this in terms of energy, it takes energy to climb up this rock. When effort and energy are exerted, you do work to climb up the rock. You give yourself energy. So when you're standing up here, you have the energy that you essentially gave your body from climbing it up. That's where the energy went, to lift you up. Now you can release that energy by falling back down, as this person is doing. So you are losing PE, and it's turning in to KE till it hits the water, and then the kinetic energy turns the water to splashes. Some of the energy goes to splash the water, some of the energy slows you down, and then the energy is transferred. That's the whole idea here, is that we have energy being transferred. But I want you to think about energy transferred in some of the older stuff that we've done, because I can't think of a more fitting way to end this year than to talk about little Susie one more time. So I want to be 100% clear about this. We know that as an object falls to the ground, it transfers its potential energy into kinetic energy. It loses height and gains velocity. So that's what I just said. You have been showing me that in the Google Forms. You kind of understand that. It's really important that we know that when an object falls, it loses potential energy and gains kinetic energy. When you throw something up into the air, right? When you throw a ball straight up into the air, it leaves your hand with a ton of kinetic energy. As it goes up into the air, it slows down. So it's turning the kinetic energy into potential energy. Because it went up, the energy gave it height. And then it turns it right back down into the kinetic energy. So like that's almost like vertical throwing, right? When you throw something into the air, the speed it leaves is the speed it returns, because energy is conserved. If you throw it going up with 3,000 joules of energy, it's coming back with 3,000 joules of energy. And maybe 3,000 joules of energy translates into 10 meters per second. Wait a minute, Bazooda. Are you saying that the things that we learned early in the year are going to come back again now? Why, yes. Here's little Susie at the edge of a cliff, about to drop a ball. And let's say this is free fall. If you remember some things about free fall, I want to get a color that you can see better, probably yellow. Yep. There you go. Free fall means that the V naught is 0. When the V naught was 0, I said you could use V equals AT, and D equals 1/2 AT squared. These are the from rest equations, if you remember from back then. It's really just the kinematic equations with the V naught is 0, and the whole part cancels out. In fact, I never even needed to teach you these equations like that. But whatever. Just in case you don't remember, it was V equals V naught plus AT. Oh my God, yes, they're back. They're back. Oh, I've missed them so. I have missed them so much. Again, I've said this before, but just to reiterate, when the V0 is 0, this part of the equation cancels out, and you're left with that. This part of the equation cancels out, and you're left with that. Done. So little Susie drops the ball, and it falls, and it's going to the ground. What is the velocity at time 0? What is the displacement at time 0? Okay? Hasn't left her hand. So it's not moving, it's not going. It hasn't gone anywhere. You are more than capable of opening up your notebooks, checking this out, and seeing this exact chart, because we have wrote this down dozens of times back in the day of 2019. It falls, it's in the air for 1 second, so its velocity is accelerated by gravity. Negative 9.8, 19.6, 29.4, 39.2. Yeah, and let's call that meters per second. So, and then the displacement, again, just keep plugging into this equation right here. Negative 4.9, negative 19.6. Wait, Vizzuto, how are you getting these numbers? Oh, fine, I'll show you. All right, velocity, it just changes by 9.8, negative 9.8 every time. To get the displacement, I'll do displacement for 3 seconds right here. D equals 1/2 AT squared. A is gravity. God, it feels so easy now. Remember how hard this was back in the day? 3 times 3 is 9. 9 times negative 9.8, and take half of that. You should get negative 44.1. Nice. So you're just plugging it in. The acceleration never changes. You're just changing the time. So this is going to become negative 78.4. How can I do that in my head? It's one of those tricks. 1 second. So don't even worry about it. But 5 minus 1, 5 minus 1.1 squared. Don't even worry about it. But don't even worry about it. So the equation right here. Love it. So we've seen this. This isn't new. Okay. So how's this going to connect to energy? I feel like you showed me that picture of the guy jumping off the cliff for a reason. I did. Now let's go ahead and examine the exact same thing that we just did. Here's little Susie dropping the ball. I filled in the free fall chart already. We did that in the previous slide, and we did that a lot back earlier in the year. So hopefully there's no questions about this part right here. But let's go add some new columns to this. Let's say we're dropping a 4-kilogram stone off a 90-meter cliff. Oh, okay. Well, if the cliff is 90 meters, what that means is that's the height of the cliff. So that is the height of our starting position. Well, this is actually going to be really easy. This one is really easy because when you drop something from rest, all of its energy starts in potential and turns into kinetic. So to get the potential energy, you just do mass times gravity times height, or 4 times 9.8 times 90. Type that in the calculator, gives you a potential energy of 3,528 joules. Because the velocity is 0, the kinetic energy is 0. So if I add these two up, I get 3,528 as my total energy. Awesome. I know that every spot is going to have the same total energy. They're all going to be 3,528 because the total energy never changes. All right. Well, okay, so I don't have the height for the next spot, so how can I do it? There's 2 ways you can do it. I'm going to show you this way first. I do have a velocity though. So I can use the velocity of negative 9.8 into the kinetic energy equation. So negative 9.8 squared, and remember, a negative squared is a positive. You must be smarter than your calculator. You must be smarter than your calculator. When you square a negative, it turns positive. So negative 9.8 squared times 4 times a half. Oh, okay. So I'm getting a (192.08 joules. Okay, what do I do with that? Well, I could subtract it from the total to get the potential energy. And that's going to be 3,335.92. Okay, a little out of space, but you get the idea. And now what I can do is this. I can use the PE equation to solve for the height. So I could say that 3,335.9. Oh, I changed colors just like in class, just randomly changing colors for no reason. I love it. 4, 9.8 H. I have every bit of confidence that we know how to go ahead and divide by that. And we should be getting a height of 85.1. So we could work backwards like that. Wait a minute. How does displacement connect to height? How does displacement connect to height? Don't forget the definition of displacement. Displacement is from where the distance from where you start to where you end. So you can think about it like this. Displacement is your height, the height where you are, minus the starting height, where it's from. Science always does final minus initial. So what do I mean by that? So let's look at it in this question for 1 second. If I am at 85.1, okay, and I started at 90, what is 85.1 minus 90? Negative 4.9. Or another way of thinking about it is that I started at 90 and then I went negative 4.9 and ended up at 85.1. It's really important that you understand how height and displacement are connected. Because I know what you're going to do. You're going to be like, oh, well, that's easy. You just keep subtracting the displacements. And I know that someone out there, some ill-fated physics student is going to say, oh, to get the height for the next one, I'm going to do 85.1. And then I'm just going to minus 19.6 because that's the displacement. And I want you to know, if you do that, it is wrong. Because displacement is always relative to the starting height or the starting position. So you can't do 85 minus 19.6, but you could do 90 minus 19.6 because displacement is relative to the starting height. You did not start at 85.1, you started at 90. So if I do 90 minus 19.6, I get 70.4. Okay, once I have that height, I can do times mass times gravity. I can get the potential energy of 2759.68. Then I can do that minus the total energy of 3,528, and I can get a kinetic energy of 768.32. Well, let's look at the trend. Is the potential energy going up or down? The potential energy is going down. Is the kinetic energy going up or down? Potential energy is going up. When little Susie drops the ball, does that make sense? Surely it does. So There are so many ways and so many strategies for solving this. I do not want you to feel locked into only doing it one way. I am not going to solve the other two because I know you have the ability to do that. You can use the velocities to get the kinetic energy, subtract to get the potential energy, and solve for the height. Or you can use the displacement and the starting height to get the potential, to get the current height, to get the potential energy, to get the kinetic energy. So many things to do. Oh, Bazooka, this doesn't seem so bad. But remember vertical throwing? Vertical throwing brought me such joy, and it brought such pain and strife to some of my students. But vertical throwing is the exact same thing we just looked at. But instead of using, in this case, the initial velocity is not zero. So we could use the equations v equals v naught plus at, and we can use the equations d equals v naught t plus 1/2 at squared. Remember that d is the displacement. So what can I fill in right away? Oh, by the way, I'm so sorry. The mass is 2. I forgot. I have to type that in. The mass is 2 kg. We'll eventually get to problems where I don't give you the mass, and you'll be able to use information from the chart to solve it. But not yet. That'll be in your homework. So let's go ahead and look at this. I know the velocity is plus 19.6. Gravity is negative 9.8. So if I just do 19.6 minus 9.8, I chose 19.6 for a reason. I wanted to make it a little bit easier. I wanted to illustrate a couple of points here. Hopefully we remember, all these meters per second, that means that it's in the air for 4 seconds. It's at the top of the path when it's going 0. Let's see if that makes logical sense in terms of energy, though. Now, let's solve a few more things first. Let's go ahead and get the potential energy. Now, I said the mass is 2, gravity is 9.8, and the starting height is 40. So it's like she is, can we visualize what's happening here? Here's the thing. So she's on the edge of a cliff, and she throws the ball up, and the ball comes down. The ball comes down, and she catches it. It doesn't fall this distance here. She throws it and catches it. So this distance, it just never goes. But if she didn't catch it, it would have the potential to fall that distance. Okay? So in this case, the potential energy is 784 joules. The kinetic energy is, this time it's not going to be 0 because we're not starting from rest. So we can do 19.6 squared times 2 times 1/2. So we can get 384.16. And then I can add that, and I can go ahead and I can get my TE. Huzzah! Once I have this, I have it for all of them. The total energy is never changing. It will be the same throughout the entire time. So, okay, what little things can I do now? Well, look, 2 seconds is such an obvious thing. If I know that the velocity is 0, I know that the KE is 0. That means I know that the total energy here is the potential energy here, because with no kinetic, the total energy is the potential energy. All right? So I can go ahead and use that potential energy to solve for the height. I plug that into the PE equation. I divide it by 2, the mass, divided by gravity, and I'm left with the height, which is 59.6. Okay, remembering what I knew from before, displacement is the ending height minus the starting height. So my displacement is going to be positive. This time it's positive because it's going up above my hand, 19.6 meters. All right? So I just filled in that row. I'm just trying to show you a variety of other ways because I know some of you are going to go ahead and be like, Bazzuto, can't I just take this equation, plug it in for this column every single time, and just get the displacements? Yes, absolutely you can. Absolutely you can. I don't want to take that away from you, but I want to show you other ways of doing it. Tell you what, now we'll do it that way for 1 second. We'll do it this way for 1 second. So I'm going to plug in, we're looking for displacement. The initial velocity is 19.6 times 1 second plus 1/2 times negative 9.8 times 1 squared. By the way, you have to use negative 9.8 in the kinematic equations. I typed all that information here, and I got displacement of plus 14.7. Awesome. So what's my height? What's my height if my displacement is 14.7? Oh, well, if I start off at 40 and I went up 14.7, this should be 54.7. Simple. Now, I can solve for the potential energy with a height. 54.7 times 2 times 9.8 is 1072.12. And then I can minus that from the kinetic energy, minus, I'm just typing that in the calculator real quick. You get what, like 96.04 joules. And we're done. Wait a minute, Zito. We have 2 more rows to fill out. Well, no we don't. And I want to illustrate a point. And I need you to be open to playing around with these ideas. The velocity here and the velocity here are actually the same. No, one's going up and one's going down. But when you use the KE equation, KE, and I said energy doesn't care about direction. And we can mathematically know that because if the velocity is square, whether it's positive or negative, the square is going to just cancel all that out. So velocity, in terms of kinetic energy, doesn't depend on direction. It just depends on the number. And this makes kind of sense. So that means the velocity here is going to be 9604. Do you remember how I said that vertical throwing was symmetric? Pay attention to patterns. Pay attention to patterns. Hey guys, let's think about this in terms of potential and kinetic energy. If you throw the ball up into the air, right? You throw it up, it gains potential. And when it's at the highest point, it has no kinetic energy because that's when it stops moving just for a brief second. Think about how everything that we learned actually fits with this energy stuff. Let's just pretend little Susie didn't catch it. Let's pretend she let it fall. The displacement would turn negative. The height, would the height ever be negative? Could the height ever be negative? Well, if the height's negative, that means you're underground. That doesn't really make sense in terms of a situation like this, because you're not going to throw a ball and have it go underground. It's going to hit the ground, it's going to stop. And I'm going to be like, no, no, no. Don't be like, well, if you throw it fast enough, just let's think practical. It's just going to hit the ground and it's going to stop. The potential energy will continue to decrease and the kinetic energy will continue to increase, but the total energy will never change. connections. So, in a way, there's nothing that's actually new. But what I am going to do is I'm going to ask you to apply some of these concepts to situations and problems that we did not explicitly solve in the video today. I want to see what you can do. I want to see you kind of struggle with this and think about the interconnectedness of all these variables and all these values. So, don't just give up. I will be here if you don't know how to start and you don't know how to approach. But I don't want the first question to be like, Pizzuto, we didn't do this exact problem on the video, so how can I do it in the homework? You can. You have so many tools in your toolkit now to solve things. Don't be afraid to try something and to see how you can make it work. You got this. But if you do need help, I will help. I will help you. If you're like, okay, I didn't have this, but I tried this, and I couldn't figure it out. That's a much better way to come at me than be like, Pizzuto, I haven't seen this before. We can get through this. Oh, by the way, 2 weeks from now, seniors are done. So, I mean, not seniors are done. Seniors' grades get printed on their final transcripts 2 weeks from today. So, just throwing that out there to the seniors. Juniors, we're going to have some more time. But seniors, just so you know. Next week, we're only going to have one assignment. It's going to be a test. It's going to lock your Chromebook on all the energy stuff that we've done. So, I'll talk more about that later this week. But just so you know, that's coming. And because your Chromebook will be locked, it might be a good idea to have some notes because you won't be able to pull up the videos to the Chromebook. Yes, you could pull it up on your iPhone, your smartphone, whatever, and you can go ahead and pull it up and look at it that way and do all that. Sure. That's a pain. You might want to start making some notes on some of these things so that when the equations come, you know what to do. All right, guys, good luck, and I will see you next time.